Hey you guys, this is Mr. Sal. Thanks for watching. This is a lesson on similarity, which is a little bit different than congruent. That's our lesson for today, so thanks for watching. Please subscribe, comment below, and like the video. Thank you. Before we start the lesson right here, we've seen the symbol before, but the symbol for similarity is this little swish looking thing right here. So if I wanted to say, for example, that side length or maybe triangle ABC is similar to triangle DEF, then I would put a little similarity symbol between these. And now I know that these two triangles are similar. In the Unit 10, we discussed congruence. Actually, it's kind of Unit 11, but whatever. Two figures are congruent if one can be obtained from the other by a rigid motion, rotation, reflections, and translations, or a sequence of rigid motions. If you can move one of the figures using one of these transformations or a series of these transformations so that it fits exactly on the other one, the two figures are congruent. In this section, we have seen problems where two figures are similar. In 7th grade, you learned that two figures are similar if they have the same shape. They may or may not be the same size, though. In 8th grade, we define similarity in terms of transformation. Two figures are said to be similar if there is a dilation or sequence of transformations that includes dilations that take one figure onto the other. While studying dilations, we have learned that 1, a dilation creates a figure that is the same shape as the original figure but a different size. 2, the measure of corresponding angles is the same. And 3, the ratio of corresponding sides are all the same. Since similar figures are produced by dilation, these properties, as well as some others we observed, also hold true for similar figures. Yes. So let's go back and revisit this problem, which we've seen before. In this picture, triangle ABC has been dilated to obtain triangle A prime, B prime, C prime. The center of dilation is the origin, which they've shown at the red dot right there. And the scale factor is 2. Because A prime, B prime, C prime was produced by dilation of triangle ABC, the two triangles are similar. We can write a similarity statement for the two triangles. You can denote that two figures are similar by using the symbol that we've seen and listing their vertices in corresponding order. The order of the vertices is written, tells us which segments and angles are corresponding in the figures. When two figures are similar, corresponding angles are congruent and corresponding sides are proportional. The ratio of the lengths of the corresponding sides is a similarity ratio. All right, write a similarity statement for these two triangles. Well, we have the first triangle, which appears to be the pre-image, which is triangle ABC. And we are comparing this to the image triangle, which is A prime, B prime, C prime. And these two are similar. So we put the similar symbol between them. Maybe we can make it look a little bit more pretty. That looks all right. Write the congruent statements to represent these. There should be 3 congruent statements, all for the ankles. For example, I've got ankle, we'll say ABC, which is congruent, that's the symbol for congruence, to ankle A prime, B prime, C prime. Alright, that was one ankle, specifically this one right here, and these. But we can also compare it to the ankles right here. So the one in the pre-image is ankle BAC, which is congruent to ankle B prime, A prime, C prime. Next up is this ankle right here, which we need to name properly. And that would be ankle ACB. And this should be congruent to ankle A prime, C prime, B prime. Now we got to write the similarity ratio for these two triangles. Well, the ratios should be the same. What I'm going to do is I'm going to compare the image to the pre-image. And then that as a ratio should be the same for all of them if it is if the two are actually similar. And then we can compare some of the values if we need to. All right, so this is the ratio that shows that these are equivalent. Well, let's compare one of them. For example, AB, which is 3, and A prime B prime, which is, that's not 3, that's 2. AB is 2, and A prime B prime is 4. So that would have given us 4 over 2, which is 2. And we hopefully remembered that the scale factor was 2. So this should always give you the scale factor. If you take a line segment from one of the shapes and divide it by its corresponding line segment in the pre-image, you should always get the scale factor like we've done right here. Works the same for, let's do C and B as well. BC is 4, 1, 2, 3, it's 3, and B prime C prime is 6. So 6 divided by 3 is also 2. That's the scale factor. In the picture below, triangle ABC has been dilated to obtain triangle A prime B prime C prime. The center of that is the origin. You know what I meant. All right. All right, a similarity statement for these two. All right, so we know we got triangle ABC, and this one should be similar to triangle ABC, but this is prime. Now we'll complete each statement. So based on what we know about similarity, the angles are the same. So the measure of angle C should be congruent to the measure of angle C prime. It's not quite accurate labeling for angles, but it'll do for now. So if the measure of angle B is 90 degrees, then that's this one right here. Then the measure of angle B prime right here should also be 90 degrees. Then A prime C prime divided by AC should be whatever the scale factor is, and we should be able to find that that is 2. Not that we really need the length radical, but you can see that this is 5 radical, and then A prime C prime is 10, so 10 divided by 2, 5 rather, is 2. So A prime B prime divided by something is 2. That would have to be its corresponding segment from the pre-image, which is AB. Right? Quadrilateral ABCD has been dilated to obtain A prime B prime C prime. Yeah, okay. I was close. Let me try again. A prime B prime C prime D prime. Oh, that worked. The center of dilation is still the origin, which they've shown in red right there in the graph. Write a similarity statement for the trapezoids. That sounds great. So we have trapezoid A, B, C, D, and this one should be similar to A prime, B prime, C prime, D prime. And that is our similarity statement. So we will complete the following statements. The measure of angle C should be congruent to the measure of angle C prime. And the measure of angle A, which is 90 degrees, which is radical, should be congruent to the measure of its corresponding angle from the image, which also is 90 degrees. Then we can compare AD, which is 8 units, to A prime D prime, which is 2 units. So AD, A prime D prime rather, which is 2, divided by AD, which is 8, would simplify to 1/4. And that is the scale factor. We see that the image is smaller than the pre-image, so it has to be less than 1. And then finally, A prime B prime equals 1/4. That's the scale factor, just like it was right here, as it is right here. But then we would have to divide it by its corresponding segment, AB. These two triangles are similar because, well, they told us that they are, even though we could find it out on our own. But we need to write a similarity statement for the triangles. So, to start out, let's look at perhaps a small one, which is triangle MNL. MNL. Now, we got to be careful with the way that we list the corresponding vertices of the triangle SRT. So, the vertice that's in the same position as M right here is T. That's the first position. So we got to start with the T. N, which is this 90-degree angle right here, we're at the 90-degree angle, must correspond with R, which is also at that 90-degree angle. L is in the same position as S because it's farther away from the 90-degree angle. That's the way you want to look at it. So we've got triangle MNL is similar to triangle TRS. You could have listed these differently. For example, if you wanted to, you could have changed it and said that maybe it was NLM is similar to triangle RST. So the order only matters that the corresponding vertices are in the same position of the list. However, whichever order you put them in doesn't really matter. We can change it up as long as we change it up correspondingly with the other one. All right, let's write a similarity statement for this quadrilaterals. So let's go ahead and identify. We'll just start with this first one. It's quadrilateral. Let's say it's RSTU. And this one would be similar to this other quadrilateral. So R is kind of at that peak right there, which corresponds with X then. Then we went down to S and T, which is kind of this obtuse angle. W is at the same position with the other one. So I got XW. And then the T corresponds with the Z. XWZ. Wham. Bam. This is our similarity statement. By the way, once you get the first two, the rest should be a piece of cake because it should go in order. R, it's going clockwise in this direction. So over here, once we see it's going counterclockwise, we just keep going in that direction. So we just want another similarity statement right here. Let's list the similarity statement for these. Now, as it turns out, and you could check this, but the sloppage for US and ST is the same, but just backwards, which means this angle is the same as these, just to start out with. The other one really doesn't matter. So, when we list the similarity statement, I could say triangle SUT is similar to triangle. Looks like S kind of corresponds with C in this case. And then it doesn't matter which order I go in right here. Cab. So if you had made this your list, this would be okay, and it means the same thing as both these, because again, these two angles are the same right here. For each of the next transformations, determine whether the figures below are congruent, similar, or neither, and we'll circle our choice, but we'll provide justification for these. So these two, if we look right here, for example, this sloppage right here is, well, we could consider that -4/1, while this sloppage right here is down 3 to the right 2, so that's -3/2. Since those two sloppages are not the same, this one is neither.
Yes.
Neither.
I got that. Wait,
Neither.
I got that.
Congruent, similar, or neither?
Nice. Similar. Wait, I thought you were just
Well, this one, we can see that this slop is the same as these. Right here. And this length is a length of 4. This one right here has a length of 8, which is good. But then we got this one, which is length of 4. So this one also should be a length of 8. So they are similar. Already. All right, what about these? Are these ones similar? Yeah, sure. We can see that this one right here
Is it neither or neither?
is
Neither.
dilation,
Either this or that.
and the sloppages are the same between the lines. Actually, they're kind of opposites, actually, which is okay. But that would make these two similar. Alright, these two are the same shape and the same size. We can see that all that happened is we took this shape right here, and then we kind of just rotated it like these. So, as it turns out, these two are congruent.